Now let's talk about the angular component of the wave function. So remember when we first introduced this, we said that we can mathematically separate the wave function into its radial component and angular component. So now we've discussed the radial component, but let's think about what this means from the perspective of the angular component of the wave function. And so this is what you may remember from previous chemistry courses as the shapes of the orbitals. And so, for instance, an s orbital, right, we think of as a spherical orbital, okay, which has spherical symmetry around the origin, and again, basically looks like a sphere, okay, where we have, where we'd expect to have varying amounts of probability of finding the electron depending on the distance from the nucleus, and it's going to have this general distribution as far as the shape of what the orbital looks like. And so remember, as we discussed in a previous video, right, what these shapes actually indicate, right, is some percentage of finding the electron within that space, right? And so depending on the definition, that might be 65% or 90%. Because if we included 100%, the reason we do this is because if we include 100%, it would have to include the entire universe, right? Because there's a probability of finding the electron anywhere in the universe except at the nucleus, okay? According to the mathematical functions, right? And so this is what the shape of the s orbital is, but then the p orbital, right? Remember we have, from previous classes, you may remember that there's what's called degeneracy. And so there's 3 degenerate orbitals, which means there are 3 orbitals with the same energy, and they have the general shape, for instance, like this, where if we use a XYZ graph, such as the one depicted here, right, this would be a PZ because the axis of symmetry, right, lies along the Z axis, all right. We can have the px, because again, the axis of symmetry lies along the x-axis. And then we can have the y, because this has a, the axis lies across. So let me get that to match a little better. According to the there we go. Okay, and so again, the axis lies along the y-axis. Okay. Now, one thing that we'll point out here now is that with these p orbitals, we also have different phases of the orbital. Okay, and so we have, for instance, a positive and a negative phase, and so we'll call this shaded region the positive region, okay, the positive phase, and then we'll call the unshaded region the negative phase, okay? Now this comes from the sign of the angular function, of the angular component from the wave function. So if you recall, right, when we look at for instance, thinking back to the one-dimensional particle in the box, right, you can have crossing points where the value of the wave function will cross over from positive to minus, okay? And so the sign, right, of the, oops, I'm on the wrong page here. The sign of the, what we call the, of the lobe, okay, is going to be determined on the wave function, the sign within the wave function, okay? So there'll be positive and negative regions, okay? And that's important for thinking about, again, interference, either constructive or destructive interference, such as what we talked about with waves, wave behavior in a previous video, okay? But the shape itself, right, as I discussed, right, is talking about a probability. Okay, so what the shape, right, is dictated on is the square of the wave function. Okay, and in this case, the square of the angular component of the wave function. All right. So again, so sine is dictated by y of theta phi, shape by y squared theta.